Hello students. This week we're going to be talking about the physical environment for life. So this will be in two parts. So the first part will be discussing the special nature of water as well as climate. The second part will be discussing more features that affect climate. So when you get the lecture, you only need to view the first part for this week, and then next class you can view part two. So when we talk about the physical environment for life, what does that mean? We are talking about the conditions that need to be present on a planet in order for life as we know it to exist. So remember, when we think about life on other planets, we are using inductive reasoning. We're basing that on the conditions that we see on planet Earth, expecting that they will be the same on other planets. And one of those things is the presence of water. That's why when we search Mars, we're looking for water. Typically, most substances will get more dense when they freeze, but not water. You can see this happening when you get a glass of ice water. The ice will float to the top. So most substances, as they freeze, their molecules slow down and become more dense, right? So they're more tightly packed together, which causes them to sink. However, water, because of its special structure, will actually form this lattice pattern that you're seeing in the graphic, and that makes it lighter, so it's able to float on the surface of the water. Our water molecule, probably the most famous chemical equation, H2O, right? So two hydrogen molecules bonded to an oxygen molecule. So water is special. That's what makes life on our planet possible. If water didn't act in this special way, we would not be able to exist on planet Earth. As it says on the slide, if water behaved like every other substance on Earth, it would steam even in the coldest places. So let's compare it to a molecule with a similar chemical structure. That's hydrogen sulfide. So one sulfide molecule, two hydrogen. Hydrogen sulfide freezes at negative 119 degrees Fahrenheit and boils at negative 76 degrees Fahrenheit, which is a pretty narrow range and also very cold, which means water will stay liquid over a much larger range of temperatures. So let's compare those two. Here we have a graph showing water molecule versus hydrogen sulfide. So our hydrogen sulfide is the column that is to the left-hand side of the screen, and our water is to the right-hand side of the screen. So if you're looking at the hydrogen sulfide, you can see the range at which it changes state. So remember when we discussed matter and state is pretty small. It's solid below, so negative 100 degrees Celsius is solid. And before it even reaches 100 degrees Celsius, it is going to change to a gas. So only about a 24 degree range of temperature change. Meanwhile, water has a 100 degree temperature range. So if you know the Celsius scale, as we talked about that last time, below 0 degrees Celsius, water will be a solid. And then it will boil at 100 degrees Celsius. So that 100 degree range of temperature means that it will be liquid for a wide range of temperatures, which makes life on Earth possible. So our electrons have what charge? If you said negative, that is correct. Our electrons will move closer to the oxygen molecule. So you can kind of see that in the graphic here, which means that the oxygen end of our water molecule will have what charge? If you said negative, you're absolutely correct. So that means on the hydrogen end, it will have what charge? Again, if you said positive, you are absolutely correct. So why does that happen? Oxygen has a particularly strong bond with its electrons. So that means it'll draw those electrons towards itself. And then the hydrogen has a very weak attraction. So basically what that means for our water molecules is they're going to act like little magnets. This is why they have such a tight bond. This is why they're able to stay liquid over such a wide range of temperatures. If you look at our water molecule, it is a bipolar covalent bond. That means that, again, it has a different charge on each end of the molecule, but it's a covalent bond. Just to review what that means, covalent bonds mean that the atoms are sharing electrons. The ionic bond, which we're not seeing here, is there is an unequal sharing of electrons. So they're still sharing the electrons, but unequally, as you can see in the image. And our covalent is like cohabiting. They're equally sharing the electrons. The bipolar structure of our water helps life on Earth. Like I said, that keeps those water bonds very tight, which means they're hard to break. Water then is considered a universal solvent. So it will break the bonds of any of our other polar molecules. So if they have a similar structure where there is a negative end and a positive end, it will break the bonds of those atoms. Whereas if it is neutral or nonpolar, it won't break them up. So when we talked about chemical versus physical change, we discussed that sugar dissolved in water is a physical change. That is because the molecules of our sugar do not break up in water. It will stay sugar. Salt, on the other hand, is polar. So when it is dissolved in water, it will break the chemical bonds, which means it was a chemical change. Again, as I said before, water's bonds keep all of the water on the planet from freezing. That's how it stays liquid for such a wide range of temperatures. And here you can see what that looks like over those different matter state changes. So in our ice, or our solid water, again, it forms this lattice structure. So very tightly bound together, meaning difficult to break, and it causes it to float. In our water vapor, the molecules are freely floating around. So some substances are hydrophilic, meaning they are attracted to water. So as I said, it is ionic. It has an unbalanced charge. It is bipolar. So you can see that in the image here. Hydrophiles are things like salt or soap. Again, they will dissolve them in water. Some things are hydrophobic, which means they repel water. Things like oils or fats. Our leaves will also do that. That's where you'll get beads on the top of leaves because they are repelling the water. So what does that mean? Some things are water friendly, some things are water fearing. That's why oil will float on the surface of water. So when we have a warmer substance, does that mean the molecules are moving faster or slower? Yep, that's right, they're moving faster. And with our water, it means it takes a lot of energy to make them move because of those magnetic properties. Because they have that polar end, or polar bond, where one end is negative and one end is positive, they're very tightly connected. So what that leads to with water is surface tension. So if any of you have ever done a belly flop into a pool and it really hurt, or seen those bugs that can run on the surface of the water, that's because of the surface tension. Again, the water molecules are sticking very tightly together. Those properties are also referred to as the latent heat of evaporation and fusion. We've already looked at this type of scale before, but this gives you a little bit better visualization of that. Again, the wide range where our water will stay liquid. So fusion is where our water will turn into a solid. As you might imagine, our molecules start to fuse together, become solid. The latent heat of evaporation, obviously where our water turns into a gas. So one very special property of water is its heat capacity, or how much heat that substance can hold. In this particular case, water can absorb a very large amount of heat. As it says on the slide, water can absorb 4 times as much heat as hydrogen sulfide, our similar chemical compound. It also has a very high specific heat, or the amount of heat that is required to raise the temperature of a substance by a given number of degrees. So, in other words, it takes a quarter of the amount to raise the heat of our hydrogen sulfide as it does for water. This is also, and we're going to talk about that, what causes some of the sea level rise, because water absorbs a lot of heat. As it does, it expands. The water molecules start to move further apart. So that causes our ocean levels to come up. Overall, for climate, what that means is water keeps the planet cool. Looking at our iBooks, the minimum temperature for the Earth is what? Yes, 14 degrees Celsius. For the Moon, negative 170 degrees Celsius. So which gets cooler? Right, the Moon. The maximum temperature on Earth, 36 degrees Celsius. The maximum temperature on the Moon, 130 degrees Celsius. Obviously, the Moon is getting hotter. So why does the Earth have a smaller range of temperatures? Water. Water stabilizes the temperature of the Earth due to its high heat capacity, or its ability to hold on to heat. It absorbs a lot of heat and keeps our planet cool. So now we're going to watch a short video about water.
hydrogen bombs and exploded them off gas and they charge up. This will probably result in these hydrogen bombs to have cohesion spread. Cohesion is the effect. Water has the highest cohesion of any water is the weakest, the rational, the strongest. The water molecules are holding themselves up together. One layer also mediated water. The deepest form of water, like there are other substances like big glass called diffusion. Water is stronger than cohesion. Properly used in one of my favorite water effect. Water purifies that is the thing that is happening all the time. And it's studied in things that exactly how it works. Thanks to its heat, the water molecules are attracted to the molecule. Without the water molecules, other molecules are drawn to the body all of the water. Thank you, baby. Certain things will be able to do energy to water. And it will continue to find gravity for the water. Second water is very much the ultimate solving stress. Water is there are more substances that can be dissolved in water than any other liquid on it. Substances that dissolve in water, sugar, salt, they are hypothermic. Very strong. When you get one of these cold water, it's strong enough that it breaks all the little pieces and all those little hydrogen. Instead of hydrogen bombs in the stomach, the water is hydrogen bombs in the hydrogen. They dissolve in the ion, and right now they're being separated into ions, like cold solid water molecules. But what happens when these molecules cannot break? Basically, what happens in that case? Strong that's where you get what we call a substance. A substance that is fearful of water. These molecules back in water, they are non-polar. They are not dissolving in water because eventually they're being pushed out of the water by water. You can call it the universal law. There's been a lot of but all this talk about water got communicated with the human service only via voice and added a staircase to the back of his house to avoid contact with his housekeeper. Some believe that just about everyone that is he just remembers as the first person to recognize the gas as a distinct substance and to determine the composition of water. Most people thought that water itself was an element. The cavities of hydrogen flammable. Reacted with oxygen then by the water. Cavities didn't totally understand what he discovered here, in part because he didn't believe in chemical compounds. Some experience with hydrogen. Nevertheless, these experiments were grounded, like it was some specific transportation. It's especially impressive when you consider the two situations what he gas. He went on not only to establish the actual composition of the atmosphere, but also to study the substance of the earth. That's the rise of the knowledge. That's all the subject of probably from other stuff. He is actually easy to figure out how to actually discover Richter's law, Ohm's law, Coulomb's law, several other laws. That's a lot of stupid laws. And if he had gotten credit for them all, we wouldn't have had real Moore's Law. So I, for one, am glad to do so. We're going to do some pretty major science right now. You guys are not really good. Go ahead, you ready? Well, yeah, I know you're not surprised by this, but you should be, because everything else in a solid is much more dense than the liquid just like water. But that simple characteristic of water, that its solid form and float, is one of the reasons why life on this planet, as we know it, is possible. No wonder that the solid water is denser than each one of us. Everything else is lined up just that well. So that's the hydrogen. So at around 32 degrees Fahrenheit, or 0 degrees Celsius, water molecules start to solidify, and the hydrogen bonds in those water molecules begin to break. They form particles. In turn, these are frozen water as ice. So in almost everything, frozen water ice. If I condense it in water, there's an escape. And we can get into some physical discussion here. We don't want to go down there with ice. Not only would it totally add up much water vapor, it would also, all this ice, sort of sink, and then swamp all of the water everywhere else would rise, and we wouldn't have any land at all. One more amazing property of water that we're forgetting. Heat capacity. Yes, water has a very high heat capacity. Probably that means nothing to you, but basically it means that water is really good at it's also very important as hard heat pumps to a dominant system. It becomes non-existent. Things like this. And it is to say, on a smaller scale, you can see water rising in temperature. It's really hot. If it's hot with no water on the stove, and how badly that goes. But then you put a little bit of water in it, it's forever freaking boiling. Oh, and if you haven't already noticed this, the water evaporates from the steam, it cools it down. Now, that's the principle behind getting but this is just another incredible thing to think about water. When my body is hot, that heat affects some of the water molecules that we think when they break those hydrogen bonds and they evaporate away. And when they escape, it actually leaving you cool. Well, this was an exercise, so I don't know why I'm saying this is a spray bottle that I keep spraying stuff with. Or maybe it's a high stress exercise. Trying to do the water. But while I'm drinking, there's the review for all the things that we talked about today. This week,
So I love the crash course, but yeah, so that video is available to you as much as you want to watch it, so you may or may not see some of those things on our upcoming exam. All right, so as he mentioned in the video, water will affect the climate on Earth. So let's discuss how that impacts climate. What is climate? Climate is very different from weather because climate is basically average weather. So weather conditions that prevail over long periods of time. Typically that period of time is 30 years. When climate scientists discuss climate, they will include all extremes of climate, including things like hurricanes or other natural disasters. It will include average temperatures during different seasons, so fall, winter, summer, the average amount of rain that that particular area gets, also the dominant wind direction, which we're going to discuss in a little bit, and whether there's fog or cloudy skies that might impact the climate. So we have discussed light, the special nature of light, and that also affects our climate. So reflection, that law of reflection that I had you guys look at, well, energy from light is reflected away from the planet. This happens in areas like our cryosphere, or the white areas of the planet, like the poles or our glaciers. We talk about absorption. This is where the light energy coming from the sun is absorbed by the planet. The planet is doing both of those things, which is going to affect our climate. So as the video discussed, water will both heat up and cool down more slowly than land. So if you live in an area with a marine environment or areas that are close to water, like Florida, you will experience cooler summers and warmer winters because the water is cool as summer begins, so it keeps the land adjacent to the water cool. In the winter, the water is still warm from the summer, so that warm air rising off of the water makes its way into the land. Land, on the other hand, will heat up and cool very rapidly compared to water. So if you're in a continental environment or somewhere far from the water, you'll experience hotter summers and colder winters. Compare South Florida to Kansas, for example. While I know it doesn't seem like it, we have a much more moderate climate compared to parts of Kansas. Kansas will experience very hot weather in the summer, sometimes going over 100 degrees Fahrenheit, where we typically do not go over 100 degrees Fahrenheit. Obviously, in the winter, they can experience temperatures below zero, where we never get temperatures below zero. I don't think that's ever happened in the history of Florida, as far as I know. What will affect our air temperature? Well, that has got a lot of different variables. So the angle of the sun's rays, the number of daylight hours that particular area experiences, the amount of water vapor in the air, which we're going to talk about later on, cloud cover in the area, the nature of the surface of the earth, so either it's land or water, the elevation or the altitude of the area, and also the direction of the air movement, which again, we're going to talk about global air circulation patterns in just a minute. Okay, so just a refresher, if you are unfamiliar with it, latitude and longitude. Those are imaginary lines. They don't exist in real life, but they give us an absolute position for a place on Earth's surface. When we talk about climate, the most important is latitude. So an easy way to remember that when we talk about latitude, so you can look in the graphic here, lines of latitude are like a ladder going up and down, north and south from the equator. They are our horizontal lines. Longitude are long lines. They are going east and west from the prime meridian. They basically divide the Earth up like a giant orange, so dividing the Earth into sections. Longitude is an effect of time, and we'll discuss that when we talk about the history of science. When we talk about climate, probably the most important is latitude. So as I mentioned, the angle of the sun's rays will affect climate. How does that happen? Well, one effect is beam spreading. So let's imagine that we have a flashlight, as you see in the image. Pretend you're a CSI, crime scene technician. You go into a dark room and you have your flashlight, you're investigating for evidence. If you aim your flashlight directly at the floor, you will have a concentrated spot of light. Well, that's not going to be very helpful most of the time. So you will aim your flashlight at an angle and the beam spreads or diffuses across the floor. In terms of radiation, that incoming solar radiation, when it diffuses across the surface of the Earth, it will make the light weaker. So as you see in this image, areas around the equator or the lower latitudes, remember that the equator is 0 degrees latitude, the sun's rays will be more concentrated. They're arriving at the Earth parallel, so they're coming straight in. At our poles, our higher latitudes have that beam spread across the curved surface of the Earth, which means it will be diffused. So the energy gets diffused across the surface, and that means it's less concentrated, which is why, now you know, the poles are colder and the equator is warmer. Another effect of those incoming rays is the filtering effect of the atmosphere, also known as beam depletion. So if you notice in our graphic, we have our Earth and the yellow circle representing our atmosphere. So as our incoming solar radiation hits the equator, the middle of the Earth, it's coming in straight and crossing through a relatively short distance. As it is approaching the poles, it must pass through more of the Earth's atmosphere. So it's not thicker at that level, it's just that the beams have to cross through more of it, which means that they will reduce in energy as they pass through that part of the atmosphere in order to reach the Earth's surface. Which means less energy at the higher latitudes. And if you're not familiar with that, the poles are 90 degrees latitude, so 90 degrees north, 90 degrees south. Our equator is 0 degrees latitude. The Earth's temperatures are also affected by Earth's movements, both its rotation on its axis and its revolution around the sun. So the Earth is inclined just very slightly on its axis, about 23.5 degrees. So as it is rotating on its axis, it of course is giving us our days. And it's making its journey around the Earth, or the sun, excuse me. So as it revolves around the sun, it will receive different amounts of incoming solar radiation. So for example, we are approaching our vernal equinox, almost there actually, and that means that the incoming solar energy at that time is equal in both the north and south hemispheres. And as we approach the summer solstice, the incoming solar energy will be greatest in the northern hemisphere. So that's why in the summer months for us, which is June, July, August, it's really warm because our Earth is not tilted towards the sun, so we're getting the most amount of incoming solar radiation. In our winter months, so December, January, February, it will be cold. As you can see, then the Earth is tilted away from the sun. So in the northern hemisphere, we're getting less sun at that time, which is why in the southern hemisphere, what we call winter is their summer. So that's all what I've just said in words. All right, so the seasons then are a result of the concentration of sunlight in a particular area. Again, that's why it's also colder at the poles than closer to the equator. Well, what about those ocean currents? As I mentioned, our air and ocean currents also affect our climate. So ocean currents help regulate the climate by bringing hot water to the poles and cold water to the equator. So very helpfully on this image, the red lines represent our warm ocean currents and the blue lines represent cold ocean currents. So for example, you can see adjacent to Florida is a red line. That is our Gulf Stream. So the Gulf Stream helps keep our climate here in Florida very temperate. I know it doesn't feel that way in August in Florida, but it is relatively temperate, keeps it nice and warm. As the Gulf Stream makes its way across the Atlantic and up into Europe, as you can see in the image, it becomes known as the North Atlantic Drift. So in parts of Europe, for example, like Paris, they have relatively temperate seasons because of the North Atlantic Drift. It's bringing warm air and water to Europe. It also affects precipitation. So I'm going to show you some maps in just a second. But our cold water currents are going to create dry conditions on the land, and our warm currents will create moist conditions, just as I said with the Gulf Stream. So here's our ocean currents, and here it is more easy to see those labels. If you look on the coast of South America, the Peru current is a cold water current. It is bringing cool water up the coast of South America. Does anyone know what large geographic feature is on the coast of Peru? You might not have known, but you might have been able to guess. It is the Atacama Desert. Cold ocean currents create deserts around the world. You can also see that as on the west coast of Africa, and you can see that on the west coast of Australia. Here you can see that as well. The Atacama Desert adjacent to the Peru Current, the Sahara Desert adjacent to the Canary Current, the Sonoran Desert adjacent to the California Current. There's another feature I want to point out. These areas are also around 30 degrees north and south latitude, as you can see in the image. That is an atmospheric effect called the subtropical high. I'll show that in more detail in just a minute. So we have hot versus cold deserts around the world. As you can see in the map, things like the Gobi Desert or the Polar Desert are actually cold deserts. So we find those at higher latitudes, also higher elevations. So the Gobi Desert is in an area called the Tibetan Plateau, which is a very high flat area. Also in the center of a major continent, which makes it very dry. They may also be adjacent to those cold ocean currents. Our hot deserts then are at lower elevation and low latitudes, very far away from oceans, things like the Sahara Desert. I have a graphic that didn't work on the last slide, so we'll move on. All right, our global air circulation patterns. So the main ones that I want you to be aware of are the intertropical convergence zone, which is around the equator, and the subtropical high. As I said before, those subtropical highs occur roughly around 30 degrees north and south latitude. Our intertropical convergence zone typically lies around the equator. It shifts seasonally, so in the summer it will shift a little bit more to the north, and in the winter, for us, it shifts to the south. And we'll talk about why in just a minute. But around our intertropical convergence zone, as you can see in the image, our tropical winds converge. So those winds are warm and moist. Well, then as our water or our moist air collects, it rises. As you might know, hot air rises. As it starts to rise aloft into the atmosphere, it becomes cooler and drier. So it starts to descend around 30 degrees north and south latitude. That creates the subtropical high. So that creates the images or the landforms that you see in this image. So across the globe at about 30 degrees north and about 30 degrees south, you will find deserts. So that combination of cold water current and the subtropical high creates deserts globally. Around the equator, you will find rainforests. So you see that in the image, the Amazon, Congo, and the rainforest of Southeast Asia. Now you can read satellite images. Yay! The atmosphere also regulates our climate via the greenhouse effect. While we typically discuss the greenhouse effect as a negative effect, it is actually necessary for life on our planet. How does the atmosphere help regulate climate via the greenhouse effect? Well, those greenhouse gases that we've heard about so much actually absorb heat, which keeps our planet warm. Again, that's necessary for life on Earth. It's only when they become excessive that it becomes a problem. So as you can see in the image, sunlight is passing through our atmosphere. Some of it gets reflected, some of it gets absorbed. The physical terrain of an area will also affect its climate. This is especially apparent through orographic precipitation or the rain shadow effect. As you see in my graphic, wind rising off of the water is carrying moisture. It rises aloft, it's forced up where there are mountains or other very large physical features. As it rises up, it condenses and falls as rain on the windward side of the mountain. In the rain shadow, or on the leeward side of the mountain, it will be dry. Let me show you an example. This is the state of California. And these are the Sierra Nevada mountains. Very beautiful, not just beer. On this side, we have the John Muir Wilderness. So that is the windward side of the mountain. In the leeward side, Death Valley. John Muir Wilderness, beautiful, green, lush. Death Valley, dry, and everything dies there. One of the driest spots on Earth. So obviously it can have a very dramatic impact on the climate of a region. Why do you think it's so cold on Mars? If you guess that it doesn't have an atmosphere or an ocean, you are absolutely correct. Why doesn't Mars have an ocean or an atmosphere? Thinking about its mass, for example. That's right, it doesn't have enough mass or enough gravity to hold on to water. Now, it does have a very weak atmosphere, and we have done some space exploration that has shown that there is possibly frozen water on the planet, but as the situation stands currently, there's not gravity as we would experience here on Earth, and it doesn't have an atmosphere like Earth does. So on Earth, there actually were 3 different atmospheres. So our climate history includes an atmosphere that was primarily composed of hydrogen. Remember, hydrogen and helium are the most abundant elements in the universe. Eventually, those things became carbon and nitrogen compounds, so they bonded together. As oxygen formed in the atmosphere, we saw the formation of rust. So remember, rust is actually iron oxide. So it's a chemical change where our iron, part of those molecules, bond with oxygen and form iron oxides. Oxygen can actually be pretty corrosive, and excessive oxygen will kill you. But we came up with the perfect balance, which allowed life to evolve in the form as it currently exists. So there are a few other factors that affect climate, such as plate tectonics and land formations, as well as biogeochemistry. These are not in the textbook, so make sure that you're taking notes. That was part 1, so you can stop here if you like, or you can continue to hear part 2. So in part 2, we'll be discussing landforms and geochemical cycles. Wegener was the guy who came up with plate tectonics theory. He noticed that there was a movement of our plates, or they seemed like they might have fit together as a jigsaw puzzle, and eventually realized that while they were once joined together as Pangea, they have now drifted into their current positions. So different movement of plates creates different landforms. At divergent plate boundaries, so that's where our plates are moving apart. It's not just a movie, it is a plate boundary as well. The plates move away from each other and create new Earth's crust. So in areas like the Mid-Atlantic Ridge or the Great Rift Valley in Africa. Transform plate boundaries are where our plates are sliding horizontally past each other, just like we see in California. So think Titanic and the iceberg. One plate is grinding up with force against the other. Faults are fractures in the rock along which there has been movement of our plates. Convergent plate boundaries are where our plates move together. That will create things like deep sea trenches and mountain ranges. Our deep sea trenches will form in areas of subduction. So this is where our plates, one plate is forced under another. So typically the denser oceanic crust is forced below the lighter, more buoyant continental crust. Around those plate boundaries, we'll see earthquakes and volcanic activity. That's actually how you might realize, hey, there's a plate boundary there. In the Ring of Fire, which we find in the Pacific, there is numerous volcanoes, earthquakes, also tsunamis. So this is our ring of fire. Everywhere where you see a red dot is an active volcano. We'll also get chains of islands that form along those plate boundaries. As it said on the last slide, why might people live in an area where there's active plate boundaries and they know there might be earthquakes or volcanic eruptions? Scientists really haven't been able to answer that question for sure, but knowing that those areas are beautiful landscape-wise and people are attracted to that, but also volcanic material is incredibly rich, so it helps feed plants. Especially in the tropics where the soil is poor, people might be drawn to an area where there is volcanic activity because that ash can make the soil more fertile. So most of you have probably seen this at one point in your life, but this is the structure of our Earth. So the core, the mantle, and the crust. So our core is relatively solid. There is some liquid parts there. As you move further out, most of it is that liquid mantle. And that's really what causes our plates to move around. They're moving around on that molten rock that is our mantle. And then the outer part is our crust, where those plates are. And they are all moving up and bumping up against each other. So as you see in this picture here, our oceanic crust will meet at the continental crust. And most times that oceanic crust is forced under the continental crust. So how do they move? Why do they move? We're actually not quite sure. We think what's happening is another convection cycle. So remember, in convection cycles, at the bottom where it is very warm, it will get superheated and high flows to low. We know that principle. So that hot molten rock will move towards the surface of the earth. And then as it does that, it starts to cool down and pushing those plates apart and then forcing them up against each other. So there are the plate boundaries of the earth. Where the arrows come together, they are convergent plate boundaries. So again, you might see things like trenches, mountains forming, island chains forming, like the Aeolian Islands, which is up here at the North American plate. If the arrows are moving apart, it is a divergent plate boundary. So there we'll see things like the Mid-Atlantic Ridge. As you can see, several of those plates moving apart from each other, the North American plate and the Eurasian plate, the African plate and the South American plate, moving away from each other. And if you see the arrows moving horizontally past each other, as you see on the coast near California, it is a transform plate boundary. So that's a special type of convergent plate boundaries where, again, the plates are meeting up against each other and grinding past each other with incredible force. So there's that whole system across the Earth's surface. So where our plates are diverging, as you see along the oceanic spreading ridge, the plates move apart. As they do that, they push the other plates up against each other. So the oceanic plate is subducting or going under the continental plate. Where that happens, as you can see, incredible amounts of friction, meaning there might be volcanoes and mountains forming. In the water, where one oceanic plate is forced up against another, you will get island arcs and volcanoes. How does that affect our climate? Well, when the plates move apart from each other, it brings heat to the surface of the Earth. When those plates move apart or together and they create volcanoes, what happens is you'll get a violent volcanic eruption, and that actually will cool the planet. When it does that, that material is released into the air and is now in the atmosphere, which cools down the planet. So that is how plate tectonics can both bring heat to the surface of the Earth and then indirectly cool the planet. So what's another reason why Mars is so cold? Yep, Mars has no active plate tectonics. So now we will watch a video about earthquakes. It's very short. The other issue that might occur as a result of the movement of plates are tsunamis. Just as I said before, when plates move up against each other, that is a possible impact. A tsunami then is a sea wave that is caused by an underwater earthquake, underwater landslide, or underwater volcanic eruption. As you can see in the image, that was actually from the 2004 Indian Ocean earthquake and then tsunami. That was an incredibly destructive tsunami which killed thousands of people. So this is actually, as I said before, a classic example of potential to kinetic energy. So our waves will start in the deep ocean as small waves, but as they enter shallow water, that friction causes it to start to build up and not crest and break like a normal wave, but become basically a wall of water. So we have just another short video about tsunamis. So that was our tsunamis. Again, something very devastating to those areas, particularly in the Ring of Fire. So our volcanoes, as I said before, will usually occur at plate boundaries, but also at hot spots. So hot spots are thin spots in the Earth's crust. So initially, when Wegener came up with the theory of plate tectonics, he couldn't understand areas like Hawaii. Hawaii was not at a plate boundary. Why were there islands there? Why was there volcanoes there? It wasn't until the 1940s when a U.S. naval officer was stationed in Hawaii who was studying seafloor spreading they understood about hot spots or thin spots. So again, that is a thin area in the Earth's crust which allows molten material to reach the surface just like our Hawaiian Islands. At those areas, it creates different types of volcanoes. So just wanted to be clear here that this is just a very simplified version of the different types of volcanoes. But the two basic types are strato/composite volcanoes or shield volcanoes. So our stratovolcanoes are volcanoes like you might see in the Pacific Islands, in those areas where we have our plate boundaries. They tend to have very steep sides, as well as are the most likely to be explosive. So when you imagine those volcanic eruptions where the top blows off of the volcano, it's the stratovolcanoes. Shield volcanoes are like what we see in Hawaii. They tend to be non-explosive with very gently sloping sides. They're cone-shaped versus tall and pyramidal. While I said they're non-explosive, they can explode. They just tend to not explode with as much volcanic force as our stratovolcanoes. However, we did have volcanic eruption here in the United States. That is Mount St. Helens, which erupted in 1980. That volcano erupted with such force that it killed, I think it said 200 people, and the ash plumes spread out, as you can see, throughout a good portion of the northwestern part of the United States, and obviously also into Canada. So when that occurred, we saw atmospheric cool down. As I said before, volcanic eruptions can cool down the planet. It allows ash to enter our atmosphere and other material, which filters the effect of the incoming solar radiation, and cools the planet. So sometimes that molten rock may not reach the surface, but solidify underground, which creates other types of underground features. And then other times it may not form a volcano, such as the Deccan Plateau in India. All right, let's talk about climate change. How do scientists actually study climate change? Well, there's a couple different ways that we might study climate change. So first is through the use of ice cores, as you can see in the image. When you use an ice core, we're looking for trapped gas in the layers of ice, especially carbon. We also can use satellite imagery. When we do that, we're looking at typically ice sheet thickness or ice sheet movement. So are the ice sheets breaking away? Are they becoming thinner? We can also use things like scanning electron microscopes and mass spectrometers to analyze the gases that are trapped in ice or sediment. Again, that tells us the nature of the atmosphere at the time when that gas was trapped or that sediment was placed in the earth. All of those things can tell us things about how is the planet warming. I'm going to show you these links in a separate video. I will come back to that point. But here is an example, atmospheric carbon dioxide. So we use things like, again, ice cores or sediment cores to show atmospheric carbon. As you can see, we start at about 400,000 years before 1950. At that point, up until 1950, atmospheric carbon had never been above 300 parts per million. So carbon dioxide in the atmosphere was not above 300 parts per million. After 1950, atmospheric carbon went to its current level, which is at 400 parts per million and climbing, which means the planet may get warmer. Remember, carbon dioxide is a greenhouse gas. Greenhouse gas increases the temperature of the Earth. I mentioned in the very beginning of the lecture that we'd be talking about water vapor. One of the most predictive things in terms of increasing temperature is actually water vapor. Water vapor really holds on to heat, as does carbon dioxide. However, water vapor will quickly disperse. Water vapor does not hang out in the atmosphere, but carbon dioxide does. Any carbon dioxide that we put into the air will stay there. It stays there for about 140 years. Now, carbon dioxide is part of our carbon cycle, and that's a naturally occurring cycle. Remember, our Earth is a system. It's a closed system. But what that means is that if we put excessive carbon dioxide into the atmosphere, it's going to stay there, and it takes a long time to go away, which is why we're seeing the problem with increased temperature. Let's talk about biogeochemical cycles. So this is how chemicals and elements move in the different spheres of the planet. So we have the asthenosphere, or the anthrosphere, excuse me, which is where humans are, or other living creatures. The biosphere is typically things that are not human. The hydrosphere is our water cycle, and the lithosphere is our Earth itself. Those things together are biogeochemistry. Our water cycle, I won't spend too much time on this because you're all fairly familiar with that, but just knowing that, again, our Earth is a closed system, so water moving around the planet is going to stay in the same amounts because it is the planet. So it's a closed system. So that water that's evaporating into the atmosphere, that water vapor, can increase the temperatures of the Earth. Because remember, water vapor is actually really good at holding on to heat. But it changes really quickly. It can change within hours, unlike our carbon dioxide. This is our nitrogen cycle. So our nitrogen cycle is, again, part of our atmosphere and crucial for life on the planet. So atmospheric nitrogen is not in a form that plants or animals can use. So what happens? Well, nitrogen gets fixed by bacteria that are in the roots of different plants or in the soil. Then that bacteria can process our nitrogen into a different form, which is ammonium. You can see that as ammonification. As they continue to do that, it will also change it into another form, which is nitrification, which changes our nitrogen into nitrites. They continue that process and then change the form of our nitrogen yet again to nitrates. From that point, plants and animals can consume the nitrates. So that's a very valuable fertilizer and necessary element for our plants and animals. As our plants and animals die, they are broken down by decomposers, so bacteria and fungi in the soil, and again, to help change that nitrogen into the form that we can use. Eventually then, it can be released by our bacteria to create more atmospheric nitrogen. So as you see in the graph from 1920 to 1980s, typically our naturally occurring nitrogen fixation happening in the background is relatively low. But as we have increased using synthetic fertilizers, which include nitrogen, or typically nitrates, I should say, also finding that in our legume crops and in manures, as well as fossil fuel combustion, we have greatly increased the nitrogen in our soil and in our atmosphere. What that means for our soil and our waterways is that we'll actually, that's why we see those plumes of algae. I don't know if you guys have seen that on the news, but where we get the blue-green algae that occurs, that is because of nitrogen, excessive nitrogen. This is our carbon cycle. So our carbon cycle is probably, again, a cycle that you are familiar with. So in our cycle here, you'll see carbon stores where carbon is being held, as well as processes where it could be released. Our atmosphere, of course, holds on to carbon. But various organisms on the planet need carbon. So carbon gets held in sedimentary rock, which can be processed into oil, gas, or coal. Soil actually holds on to a lot of carbon, as does our vegetation. In fact, plants and soil hold on to more carbon dioxide than our entire atmosphere. So we don't really want to destroy those things or we'll be in trouble. Our ocean also absorbs carbon. Things that use carbon include things like phytoplankton. Phytoplankton and other organisms in the ocean use carbon to help create their shells. When those things die, they will sink, and those also become limestone and hold on to carbon. Our phytoplankton also use carbon. They breathe it in just like plants. Well, other things like animals and humans will breathe out carbon dioxide. And as we die, that happens too. Those are naturally occurring things. All those processes are natural and so not increasing the global atmospheric carbon. But things like burning fossil fuels or burning of forests have increased the carbon dioxide in our atmosphere. So the graph to the right is called the Keeling curve. The Keeling curve was something that was began by Dr. Keeling in Hawaii, and he started measuring atmospheric carbon dioxide. He began that in the 1960s until the present. As you can see, atmospheric carbon has increased every decade since he started measuring it. Why? Because of the burning of fossil fuels. This is the rock cycle. Again, a cycle you are most likely quite familiar with, so I won't spend too much time with it, but just knowing that that is how we release minerals into our soil actually is through the weathering of rock. And then finally, thinking about the study of biogeochemistry. It has been limited to the Earth itself. However, now we are starting to study the biogeochemistry of other objects in our solar system. Okay, so that is it for Science and the Environment lecture. I will have another short lecture about climate change. You can watch all of this together or separately, and then go to Canvas to complete your assignment.